All right, so we're going to continue our journey into the world of probability by looking at counting properties and some rules associated with it. The first task is to deal with arrangements that have some sort of repetition in it. So the rule here is if I've got R number of choices, and I'm going to repeat this, R selections at n number of choices, then the total number of possibilities is n to the R power. So let me illustrate this out a little bit easier with some numbers here. So let's say I want to do a 7-number license plate and keep track of how many total different combinations of digits there are. So how many for the first position? So look at all 7 places here. Okay, so how many for the first? Well, there's 10 digits possible. So for the first spot, I could have 10 numbers. For the second spot, I can have 10. For the third spot, I can have 10. And so I can keep multiplying by 10. Okay, so this translates to 10 to the 7th power, which works out to be about 10 million. And this again assumes there's no repeats and stuff like that. A little bit more specific is when we are dealing with what's called a permutation. Whenever the following conditions are applied, so all selections come from a single group, no item can be picked more than once, and the order of the arrangements matter. So permutations, I like to think about as sort of a presidency. If I'm going to grab 3 people out of a group, and the first person I grab is the president, the second person is the vice president, the third person is the secretary. If you get picked first or third, it's going to matter to you, right? Order of being picked is matters. So permutations to me sounds kind of like a president. So the formula is total number of permutations possible for n items is n factorial. So total permutations with n items is n factorial. Okay, so let's kind of look at an illustration of this. Middle school principal needs to schedule 6 different classes: algebra, English, history, Spanish, science, and gym, in 6 different time periods. How many different possibilities are there? So there's 6 total, so 6 factorial. So that means 6 times 5 times 4 times 3 times 2 times 1. Now if you multiply that all out, you should get about 720. Okay, if we make, we make R selections from a group of n items, the number of permutations, arrangements of which matters, is defined by the following formula. So n objects R at a time is n factorial over n minus R factorial, which just translates to n times n minus 1 times n minus 2 all the way down to n minus r plus 1. Basically, we just ran out of numbers is what we're looking at. Okay, so illustration of this would be on a team of 10 swimmers. How many 4-person relay teams are there? Well, it's so the notation for this would be out of 10, permutation 4 at a time would be 10 factorial over 10 minus 4 factorial, which is 10 factorial over 6 factorial. Okay. Now for us, that just simplifies down to 10 times 9 times 8 times 7. So we've got 4 different positions. There are 10 options for the first one, 9 for the second, 8 for the third, and 7 for the fourth. Works out to be 50, 40. Now, if you want to see a little bit better how this works algebraically, so it's sort of a more advanced math course, we would take this 10 factorial. So 10 factorial would be 10 times 9 times 8 times 7 times 6 times 5, 4, 3, 2, 1. Okay, 6 factorial is 6 times 5 times 4 all the way down to 1. And then notice numbers at the top and bottom divide out. So that's another way we kind of get that 10 times 9 times 8 times 7. If an international track event has 8 athletes participating and 3 medals are to be awarded, how many different orderings of the top 3 athletes are possible? Okay, so we're looking at permutation of 8 objects 3 at a time. So 8 factorial over 8 minus 3 factorial. Okay, and that will simplify down to 8 times 7 times 6. 8 possibilities for first place, 7 possibilities for second, and 6 possibilities for third. So it works out to be 336 total options. All right, Little League manager has 15 children on her. Little League manager has 15 children on her team. How many ways can she form a 9-player batting order? So this would be 15 permutation 9 equals 15 factorial over 15 minus 9 factorial. So that's 15 factorial over 6 factorial. So using our little shorthand notation, that's just 15 times 14 times 13, 12, 11. I want to make sure I get 9 spots here. So 1, 2, 3, 4, 5, 6, 8, 9. Okay, so just make sure I got 9 numbers. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. So if we type that in a calculator, we end up with a really large number. So there are a lot of possible ways that she could rearrange this. Okay, a combination occurs when the following rules are met. This is different than a permutation. So all selections come from a single group, no item may be picked more than once, and the order of the arrangement does not matter. So in a permutation, the order does, and this one it does not. I like to think of a combination like a committee. If I'm picking 3 random people out of a group, and they're all going to serve on this committee, it doesn't matter if you're picked first or last, you get to serve on the committee. You get the same responsibilities and authority as the other 2 people picked. So combinations, think of an idea of committee. The formula for a combination, so it's n objects r at a time, is a permutation divided by r factorial, or n factorial over n minus r factorial times r factorial. Sort of another way to do that. Okay, if a committee of 3 people are needed out of 8 possible candidates and there's not any distinction between committee members, how many possible committees would there be? So I've got a combination of 8 people, 3 at a time. So that's 8 factorial over 8 minus 3 factorial times 3 factorial. Okay, so this is 8 factorial over 5 factorial, 3 factorial. So 8 times 7 times 6 times 5, 4, 3, 2, 1. Spelling that out. 5, on the other hand, is 5, 4, 3, 2, 1. And 3 is 3, 2, and 1. Okay. Now a couple things I notice. The fives, 5, 4, 3, 2, 1, that divides out, and I'm left with 3 times 2 times 1. Well, 3 times 2 is 6, so the 6 divides out, and I'm left with 8 times 7, so there's 56 ways that that could happen. Although a particular coincidence may be maybe highly unlikely, some similar coincidences may occur extremely unlikely or certain, or even certain to occur. In general, that means coincidences should be expected to occur with their likelihoods dictated by the laws of probability. All right, so sort of an interesting question. What's the probability that at least 2 people in a class of 25 have the same birthday? So this will kind of bring up this idea of coincidence. Things that we associate with just random happenstance and coincidence actually are also governed by the laws of probability. So one way that we could go about calculating this, and I'll kind of do this the long way, and then we'll kind of look at it sort of a different way of doing this. I could say that what's the probability that all 25 students have different birthdays? Okay, so you got to think, out of 365 days, that means the first guy, sorry, start from here. So we've got 25 students. The first guy's got his birthday on a certain day. Okay, that means the next student can have any day they want except for the one that the first one had. And the next student can have any birthday they want except for the other 2 that have been used up. So you kind of get this idea that we're going to go all the way down until we get 25 students later, which is 341. Okay, so we could type that in a calculator and we end up with about 0.431 on that. Okay, now why is that useful? So that basically says that in a given room, the likelihood that all 25 people have different birthdays works out to be about 43%. So what's the likelihood that at least 2 people in the class have the same birthday? Remember that phrase, at least? Well, the probability of at least one shared is the same as 1 minus the probability that no one has the same birthday. Okay, and that's the one that we just figured out. So that's 1 minus 0.431, which works out to be about 0.57. So 57% of the time, I would expect 2 people in a class of 25 to share the same birthday. So sort of think about that in a real-world context. 25 students is typically a normal class. So think about how many times you've sat in a classroom and 2 people have jumped up and said, "Oh, my birthday's today. Oh, my birthday's today." Okay, 57% of the time, that's just going to happen. And that's just the probability rules. So while we think that's just random coincidence, if you have 5 classes with about 25 students each, then you would expect more than half of your class, you'd have that scenario where students will match up and have different birthdays. Now, it's a much different question if you're asking what percent of the time does someone have your birthday. That's not what we're looking at. We're asking about what's the likelihood that 2 students have that's a shared birthday. We're not really narrowing it down to a specific day. We're just any day in general.